everyone, welcome back to my channel. This is going to be a lecture on about hydroxyl compounds. Now, what are hydroxyl compounds? Hydroxyl compounds are basically alcohols. All right, so I'll write here first, hydroxyl compounds. They are alcohols and we know a little bit about them. And I don't think a little bit, we know pretty much a lot about them. All right. Anyways, for hydroxyl compounds, any kind of halogen alkane, if you ever replace one of the hydrogen with like, let's say OH, you're gonna end up getting an alcohol, or you could say it's a hydroxy compound, okay? You can say that. Now, there are like three types of way how you can actually judge a hydroxy compound, and those are your primary, secondary, and tertiary, just like halogen alkenes. So I'll just go ahead and start with it. If you have a carbon with four parts of it attached, and but one side of it has like an alkyl radical, and the other side has like an OH bond with it, we say this alkyl radical will be able to donate the electron towards the central carbon atom, whereas the OH bond takes away the electron towards itself, making it del negative, making it del positive. And again, the positivity charge a little bit decreases because of the electron being donated by the alkyl radical, kind of decreases the positive charge, but can't do it a lot because it's just one. So it's primary, and it's also called 1-degree carbocation. Or you can say 1-degree your alcohol. Okay, it's primary alcohol. And then when you have like, let's say another one where you have like two alkyl radicals attached to the central carbon atom, it decreases the positive charge even more, of course, because you know how alkyl radicals do it. Because of its electron donating nature, it decreases the positive charge a little bit more compared to that primary alcohol. So we call this one secondary alcohol. All right. And then we have the last part of it, and that's the tertiary alcohol, where we have like three alkyl radical attached to one single carbon atom, and that's a central carbon atom. And what happens is when this OH takes away the electron towards itself, it's still negative, of course, and this is still positive. However, the alkyl radical keeps on donating the electron towards its central carbon atom, making it drastically reduce its positive charge. All right. We say that this to be this tertiary alcohol. In terms of carbocation stability, we say that this one is the most stable, and this guy right here is the least stable because here the positive charge is still exposed a lot because of the one electron being donated. It's not enough. And this one, since the positive charge drastically decreases due to electron donating to the central carbon atom, we say it's most stable. All right. Now, let's talk about one of the most important thing about the alcohols, and that's their physical property. Physical property. Now, what's about their physical property that's so quintessential? Whenever we talk about physical properties in chemistry, what we really mean is solubility in water, melting point, boiling point, and all that cases, right? Now, think about it. Think about the fact that you have like an alcohol, as in CH3OH. This part is the nonpolar part. This part is the polar part. Okay, if I write it like this, it's gonna be a little bit confusing. Let me erase this part first and straight get back to you the other part. Now, let's say you have a carbon, you have a hydrogen, you have another hydrogen, you have an OH bond, and you have like an alkyl radical, C2H5, but it's on one side of the carbon, so it's still primary. Now you have this guy. This is carbon and hydrogen bond, and they're not so polar. In order for polarity to exist between these two, they must have an electronegative difference between them. They don't have electronegative difference as much, which makes them less of a polar chemical. So, and more of a non-polar chemical. And this region, as in the carbon to hydrogen bonds region, since it's non-polar, most of its forces, intermolecular force of attraction, are induced and temporary dipoles, all right? Whereas this carbon, since it's attached to OH group, it's a little electronegative, This is polar. And since it's polar, it's more or less has its electromotive force. Why am I saying electromotive force? I'm completely sorry about it. Intermolecular force of attraction is basically due to permanent dipole, but since OH is present, it's due to hydrogen bonding. Now, hydrogen bonding is one of the most strongest intermolecular force of attractions that covalent compounds can actually do. And since they're pretty strong, they can also interact with water. So due to having hydrogen bonding and induced and temporary dipole that usually exists due to the number of electrons present in the nonpolar region. So these two make pretty intense network with nearby chemicals of themselves, and hence a lot of energy is required to break them apart. Hence, they have a very, very high boiling point. So if the question is ever asked, why does alcohol have like a very high boiling point? You have to say that other than the alkane part, they also have like an OH part, and this OH part does an intermolecular force of attraction that does hydrogen bonding. And of course, the alkane part does induce a temporary dipole, which is set up by the amount of the length of alkane chain. If you like have like here more carbons, you'll have more electron, more induced and more temporary dipole will be set up. But hey, you have like OH here, which is basically forming hydrogen bonds. And hydrogen bonding is pretty powerful. So a combination of hydrogen bonding on one corner and the other combination of induced and temporary makes it very, very stable and very interactive in terms of intermolecular force of attraction. Hence, a lot of energy is required to break these forces. Hence, boiling point is pretty high. Okay, that's the simple way of explaining why one of their properties says that boiling point is pretty high. The other property says that it's pretty soluble in water. Now, why is it so soluble in water? If you ever look at the water diagram, it's water has a bend shape and it has like a 105 to 7 degree bond angle right here. 105 to 7 degree bond angle. I don't want to emphasize on that right now. This is del positive, this is del positive, and this is del negative, and this is del negative, right? Now, when you have like an alcohol around the chemical, let's say you have like an OH bond here, and this is attached with another alkyl radical right here. This OH bond forms an hydrogen bonding interaction. The hydrogen of the OH interacts with the lone pair of the water molecule, forming hydrogen bonding, of course. This is hydrogen bonding, exactly. So when it does so, the energy right here is pretty the amount of energy released is pretty big comparatively. Hence, as a result, this happens to be soluble in water. However, the solubility keeps on decreasing if you keep on enhancing the nonpolar region. As in, I'm trying to say is, if you keep on increasing the carbon length, the nonpolar region will increase. And as a result, the effectiveness of the hydrogen bonding will decrease. Hence, there's a balance between the nonpolar region and the hydrogen bonding region. So there's only one OH. So there's like only one part of doing the hydrogen bonding. The other part is not doing hydrogen bonding. The other part is doing the completely opposite. It's going to react. It's going to have intermolecular force of attraction for induced and temporary. So if this length increases, this attraction a little bit hampers and gets disrupted, and solubility also decreases. So butanol is less soluble than ethanol. Remember that, okay? Why? Because butane has like more carbon, more nonpolar region, less of hydrogen bonding region. All right? All right. Let's move to the reaction zone. Now, alcohols, they react in pretty intense ways. But in order for you to remember all the reagents, I'm going to draw you guys basically a spider chart or like a chart for you guys to remember. So let's pick up an alcohol to work with. Let's pick up ethanol. All right, we have just chosen ethanol. C2H5OH. Wait. I think a geometric shape would do fine. Yeah, this is fine. Now, the first reaction of ethanol I would like to suggest is the combustion reaction. What happens when you start reacting with oxygen? When you start reacting with excess oxygen, it's going to form carbon dioxide gas and water. All organic compounds do so. Okay, this is my reaction number one. It doesn't require much of like, different types of reagents. If you ever decide to react alcohol with, let's say, concentrated sulfuric acid, H2SO4, or I'm saying for a few times because a lot of my students do write concentrated sulfuric acid plus. Don't write plus. I mean, if you have like excess concentrated sulfuric acid, or you could use like hot aluminum oxide, AO2O3. When I say hot, the temperature means around like 170 degrees Celsius. You will do an elimination reaction. This reaction is elimination. Elimination. Why? Because here we try to take away the OH and H. And when we do so, we create something called an alkene. We create CH2, double bond CH2, and we get rid of water. Sometimes this reaction is also called dehydration as well, because we're getting rid of water here. All right. And this reaction is labeled as combustion. Now, if you decide to react, let's say, alcohols with metals, this is going to happen at room temperature and pressure because the activation energy is pretty low, and alcohols readily react with metals such as like sodium. If you decide to react it with it, sodium is positive and it's pretty reactive compared to that of hydrogen. It's going to take the position of hydrogen and it's going to form C2H5O minus Na plus and hydrogen gas. The observation will be a gas, effervescence of a colorless gas that will cause a pop sound when an enlightened splint is placed next to a test tube with it. Now, this chemical has to be named properly, so this is called sodium ether oxide. Ether oxide. Now, if you have like an alcohol and if you have like an acid, you can easily distinguish between them by understanding the reactivity of them with any kind of bases. It could be sodium carbonate, it could be sodium, it could be any kind of hydroxide, it could be any kind of like sodium oxide, any base, just add any base. The reaction with alcohol will simply never happen. Why? Because alcohols are very poor or very bad acids because they don't want to donate their hydrogen ion at all because of the oxygen right here. It's pretty electronegative. It wants to just keep the hydrogen towards itself. All right. This is my reaction tree. So if you like have like an acid and you give all of these, you're gonna probably get a reaction. But with alcohol, never. Bases will never be able to react with it. But metals, yes, you can. Whenever you get with metal, you will be able to form sodium ethoxide, magnesium ethoxide, potassium ethoxide. Just remember the end word is an oxide. It's not the same with acid, by the way. Now, if you decide to ever react, let's say an alcohol with for instance, if you decide to react an alcohol with, let's say, your halogen alkenes for or hydrogen halides, or let's say any form of your, if you want to make react it with PCl3, PCl5, in this case, you can do so. You can easily do so. How? I'll show you. So this reaction has to have like another like dimension because this is not going to happen here. So if you ever decide to react, let's say, with PCl5 or PCl3, or let's say SOCl2, in most of the cases, you have to add like ethanol with them. But the byproducts will be same, different, but the products will be same. For all of them, you might replace the OH as a nucleophile. The chlorines will replace the OH with it, and it's going to form C2H5Cl. But the byproducts are crazy. Byproducts are different. With PCl5, the first one will give you the byproducts, like, for example, your POCl3 with HCl. The second one will be giving you H3PO4, phosphoric acid, and the third one will give you sulfur dioxide with HCl. So all of them have the same product, but the byproduct with PCl5 is POCl3 with HCl. With PCl3, it's H3PO4, and for SOCl2, it's sulfur dioxide and water. HCl. If you ever see forming a halogen alkene, but your products are like sulfur dioxide and HCl, just remember that this came out from SOCl2, okay? For the reaction between them. Now, The last reaction for this chapter is oxidation. And that's your, if this is reaction one, this is two, this is three, and this is four, and this is five. The last reaction is reaction number six. Now, for reaction number six, I think I'll have to shift the board because it's oxidation. It's pretty big of an oxidation, so we need to really emphasize on it. So I'm going to write reaction six on a different page. Let me go to a different page. Now, oxidation of alcohols are one of the most important reactions in organic chemistry because this is going to be a very important part of many, many reactions that are coming ahead. Many, many. Okay. So when it comes to oxidation, we would really want an oxidizing reagent. And for that, we would use K2Cr2O7, which obviously has a color of orange initially, and it has to be, by the way, acidified, usually with a little bit of sulfuric acid. And whenever it's done oxidizing, it's going to turn into green color. Okay. Now, let's say you have primary alcohol. So for primary alcohol, you have one alkyl radical, two hydrogen, and OH. So the rule of oxidation is you remove hydrogens first, and then you add oxygen. So in order for me to oxidize primary alcohol, I have to remove one hydrogen from the oxygen, the other from the carbon that was attached to the alcohol, but that hydrogen can't be of an alkyl radical. It has to be a single hydrogen. Now this reacts and two bonds are empty. So I form here CH3, C double bond O, and H. And water is leaving as a byproduct. Now the chemical I created right now is called an aldehyde. Now aldehydes are carbonyl compounds where the carbon is one side attached to an alkyl radical, the other side is attached to hydrogen, and we have a double bond O. Now, if you keep on oxidizing the entire chemical, and if your conditions were like heat under reflux, this chemical is also going to get oxidized. And if you decide to oxidize this chemical all over again, now, as I said earlier, the first step is remove hydrogen. But the next step is you gotta add oxygen. You can't remove hydrogen anymore. Once you remove hydrogen, the next step has to be adding oxygen. But where will you add the oxygen? Here? Here? No, you have to add oxygen to the most positive element right here, the one that has like a very small nucleus, and that's hydrogen right here. So that's like CH3, C, double bond O, and add oxygen here, it's OH. So this right here is basically an acid. It's carboxylic acid. So if you have like a primary alcohol, and if you ever decide to make the primary alcohol go oxidized under heat under reflux, you will create something called an aldehyde by removing the hydrogen first. And then when you do again heat under reflux with your aldehyde, it's readily going to get converted by adding oxygen to the H plus to form carboxylic acid. So here's a journey from primary alcohol to carboxylic acid. Now, next one is secondary alcohol. If you think about secondary alcohol right here, secondary alcohol has like one hydrogen, two-side alkyl radical, you have OH. So as you guys know, if you do heat under reflux and you add oxidizing agent in this case, it's going to remove one hydrogen from the oxygen part, the other from the spare one, and it's going to form you a byproduct as in water. And it's going to form, the spare bond electrons are going to rearrange themselves to form double bond O. One side you have alkyl radical, you have another side alkyl radical. No longer hydrogen on one corner, but rather an alkyl radical. So we right now have created something called the ketone, right? It's called a ketone. Now, this can be further oxidized because for further oxidation, I needed one spare hydrogen because the next step is adding oxygen. I already have an oxygen here and they're pretty stable on their own. So there's no spare hydrogen where I can add oxygen. So after ketone, you can't anymore oxidize because of the carbon having no longer hydrogen, the central carbon not having hydrogen for itself only. Now, if you think about tertiary alcohol right here, think about tertiary alcohol. CH3, carbon, and then you have like CH3, CH3, and then you have like your OH, and you decide to oxidize the chemical. So as you guys know, rule number one, removing hydrogen, we can remove this hydrogen, but we can't just remove this hydrogen right from here. We also have to remove another hydrogen from the carbon that's attached to the alcohol, but there isn't any. Hence, this reaction can't happen at all. So tertiary alcohols are never oxidized properly. They can't be oxidized because of them not having a hydrogen to the central carbon atom. However, when it comes to secondary alcohol, you can oxidize them, form ketone, but since no hydrogen at all, no more oxygen can be added, no further oxidation. When it comes to primary alcohol, after removing hydrogen with the oxidizing reagent in heat on reflux, we form aldehyde. And since it's still in heat on a reflux, it's gonna form acid by adding oxygen in the next step. Some questions can be like, if you don't want acid, if you want to stop at aldehyde, what would you do? Stop heat under reflux. If you stop heat under reflux and do distillation, you're just going to produce aldehyde and you can extract it out. But if you continue providing heat under reflux and no distillation at all, you're going to produce carboxylic acid whatsoever, right? That's all. That's all about alcohol's reaction. I hope you have understood the concepts and you have decided to write them all down. Then it will help you guys out. And if you guys have any question, please comment down below. All right. Have a good day, everyone.